Hello guys, good afternoon. How are you doing?
Pretty good. How about you?
Good, good. Thank you. Okay, so we have a lot to do today, so let's start now. Show you my screen. So very quickly with the model, and then we can jump into time series. Okay, guys. So what is left in the OLS model? A couple of things that we need to see. One of them is related to functional form. Okay, so remember that the OLS model, guys, one of the assumptions is linearity in parameters, linearity in parameters. Okay, so basically this implies that I can have a model like this one here. For example, beta 0 plus beta 1 x1t plus beta 2 x3t plus an error. Okay, so this is linear in parameters. Of course, also another example of linear in parameters can be something like this one here, for example. The same x1t, but now squared. So this is also linear in parameters, right? What you cannot have, guys, is beta square or beta to the power of something, okay? That's what we cannot have. And one way of testing for functional form, remember, is we have been testing, we have done the F test, the ANOVA test, the null hypothesis, there is no linear relationship, okay? So this is one first approximation of this type of identification or goodness of fit. But we have also something that is called the Ransis reset test or reset test. And this test here is going to be the one that is going to allow us to identify non-linearities in our model, okay? To identify if our model is correct. But the only issue with this test, guys, is it's going to tell you it is good or it's bad, but that's it. So you don't know what is the functional form, okay? So it's simply only it helps you only to identify the functional form, if the functional form is correct, but that's it. So imagine, guys, that we have a model like this one here, okay? So my intercept plus a couple of variables. So imagine this is your model. Okay, so the Rancid reset test works in the following way. You first run the regression, okay? Then you get the errors, and then you run the errors against the powers of y, and you're going to see in a minute. So simply different powers of y. And what is interesting, guys, is that you can realize when we do this part here, we have a quadratic form. So basically what we're saying is if yt is this one, so what we have is if I square this one here, so I'm saying simply beta 0 plus beta 1 x1t plus beta 2 x2t, okay? All this is squared. So you can see here, guys, so now we don't have, if you square these numbers or this formula here, betas are going to be to the power 2. It's going to be, we're going to have cross products. So we have a highly nonlinear model here. And that's what we're trying to do here, right? As usual, guys, my null hypothesis is gamma 1 equals 0, gamma 2 equals 0, etc. Gamma r equals 0. Right? So in words, this implies my linear functional form is okay. So this is your null hypothesis. Okay, so your test, so once you do this, your test is going to be t is the number of observations. You multiply this by the r square of your coefficient of your regression, of this regression. And then this one here is going to be distributed as a chi-square with r degrees of freedom. So what is r? Is simply the number of powers that you are using in your test. Okay. As usual, we're going to use the p-value. If the p-value is smaller than significance level alpha, this is my significance level, we simply reject the null hypothesis. Okay? Can you please open your EBUS file, the one that we were working last time? This one. Yes, this is the one. This model, the name of this file was MVA Exxon results. This is the one that we have been working last class. Do you see my screen? Do you see my EBUS?
Yes.
Okay, perfect. Yeah. So everyone, when everyone is with me, please, if you can open and let me know. Okay, so let's open the normal equation. I think we call it MVA. So this is my normal regression, guys, if you go estimate. So my model is the Exxon returns of ExxonMobil minus the day T-bill. Day T-bill is my risk-free. My risk-free, guys, is the interest rate that basically stays constant, okay? And that if I don't want to invest in risky portfolios, that's where I put my money. One risk-free rate that we use is a 3-month T-bill, okay? It's a treasury bill, 3 months. It's quite stable. So this is the rate that the people use as a risk-free rate. Then we have the Dow Jones Industrials, the returns of the Dow Jones Industrials minus the T-bill. So this is my market factor. Okay, so what I believe is that my Exxon moves with the market. So this is my first factor. I also believe that it moves with inflation. It moves with consumption, and it moves with the price of oil. Okay, so these are factors. This is an APT model. Right. Then if you run your, you can see the data here is a monthly data that goes from December 80 to January 2007. Then if you run this model here, this is what you got. Right. And then this is the one that we have been using for testing heteroscedasticity, autocorrelation, and all this stuff. Right. So now what we are going to do is we're going to test if my functional form is correct. Okay. So if my linear form is correct. You can see the first approximation here, guys. You can see the F statistic is 0, so we reject the null hypothesis of nonlinear relationship. But let's do something more proficient. So let's go to the what we are doing. Oh, the Rancid test. You go here, you go view, stability diagnostics, and then you go here, the Rancid test. Are you with me? So it's view, stability, and the Rancid test. Are you with me, guys? Okay, just click here. This number of fitted terms is simply how many powers you want be included in your regression. So remember, in my regression, I include power 2, power 3, power r. So in this case, let's do power 1 only. Okay, so this implies that we have a quadratic in the coefficients, in the parameters. So we run this one here. Let me enlarge this one. So you see, here we have the fitted square. So this is my y hat square. And the way we read this one here is this one here, guys. Remember, we use the F, and the likelihood ratio is the chi-square. Okay. So which one do you prefer in this case? When you have the chi-square of the F, which one is the one that you prefer when you have small samples?
The F more closely resembles the standard normal distribution, right?
No. Remember that the F is not normal distribution. The F looks, I will draw it in a minute. It's not symmetric, okay?
Okay.
But the F, what is interesting with the F is that it better captures the small samples, okay? Because it has two it has 2 degrees of freedom. One of them is how many restrictions I'm using. In this case, I'm using only one restriction. Do you agree? This one here, fitted square. But also considers n minus k. So this one here basically is the number of observations minus the number of parameters in your model. Got it? So the F distribution always considers the sample size. So that's why when we have small sample sizes, guys, the test to use is the F distribution. Okay. Agree with me? Perfect. Okay, so how do we read this one here? Remember, my null hypothesis is that this coefficient here, because I have only one, is equal to 0. It's statistically not significant. What do you tell me? Do we reject or not reject? The probability, remember, is the F, is the p-value. At a 5% significance level, what is your conclusion? You can use either because they are very close to each other because sample size is decent. It's large.
Reject the null.
Reject the null. Are you sure?
No, reject.
Remember, guys, if the p-value is smaller than 0.05, my alpha, then I reject the null. But in this case, my p-value 0.29 is larger than 0.05, so you fail to reject. Do you agree? So failing to reject implies that we have one, that this one here is basically equal to 0. So this is good. So this implies basically the functional form, linear functional form is okay. Make sense to you guys? Okay, questions?
Professor, and you said fail to reject, which means the fitted variable is pretty much equals to 0, right?
Yes, exactly. So what I'm saying is basically the coefficient associated, all the coefficients associated to this guy here, this one here, is statistically not significant.
Okay.
So basically we can remove this one here and then we go to our linear model. Okay. So let me go back to my screen here. And I realized that I forgot something here. This is my fitted values, okay? Y hat is my fitted values. Are my fitted values. Okay, so basically, guys, what we have done is as soon as my p-value was larger than my significance level, so I failed to reject this null hypothesis. Okay, and this null hypothesis, failing to reject this null hypothesis, is basically assuming that we have a gamma 1 is 0, gamma 2 is 0, gamma r is 0. So basically what we're saying is that our functional form, linear functional form is okay.
Sorry, Professor, can you just explain that again?
Yes. So remember, we have failed to reject this null hypothesis. Do you agree?
Yes.
So failing to reject this null hypothesis implies that gamma 1, gamma 2, gamma r are equal to 0. So this implies that this part disappears, this part disappears, this part disappears. You see? So basically what we are saying is that any other power on the coefficients, on the parameters, is not useful to explain my y. So this implies simply that indeed my functional form, my linear functional form that I'm using in the OLS model is okay.
Mm-hmm.
Make sense?
Yes, thank you.
Perfect, perfect. Okay. Let's do a couple of other things. And this one here, guys, is crucial, okay? So this is omitted variables. Sometimes, guys, imagine, okay? Sometimes you have a model that should be like that. And I will draw this one here with red ink. Okay, so imagine, guys, that this is the model. Okay, so the variables that you must include are x1, x2, and x3 to explain yt. Okay, the variability of these guys should explain the variability of this one here. However, imagine that you forget to include this one here. So you assume that you don't include this one here. Then if you don't include something that is important, guys, this is what is called the omitted variables bias. So what are the problems if you ignore one variable that is important? This is the worst case scenario for everything, guys. The parameter estimates will be biased and non-efficient. Okay, so this is the worst case scenario, remember, guys? So when we have heteroscedasticity or autocorrelation, we have unbiased, even though non-efficient. But in this case, when we are forgetting something that is crucial in my model, my coefficients are going to be completely biased and non-efficient. So non-efficient basically, guys, means that my t-test, my standard errors are going to be larger or smaller, and all my inferences are going to be terrible. Right? And also, if I want to do forecast with the coefficients that I have estimated here, everything's going to be terrible also. Make sense to you? So this is a very dangerous problem. Right? Now, the issue in real life, guys, is that you have a model normally to include variables. Okay, and if you're doing some empirical analysis, there is when the problem comes. Because if you're just doing empirical analysis, normally what you start adding variables, and then you just see what is the impact on Y. But nothing prohibits you, or nothing is going to avoid you forgetting one important variable. Okay, so that's why when we do empirical analysis, guys, we need to be sure about the variables that we're including. Okay, and always think more. I'm including all the variables that are relevant here. Should I include something more? Right? So that's why, in general, guys, what we try to do is we try to overfit the model. We try to put more variables than needed, and then we can start saying which one makes sense. Okay. Of course, everything with a sense, economic or financial sense. But the worst case scenario is that you forget something that is important that can simply put all your variables in a terrible position. Right? So let's do this example. If you have questions, otherwise we do 2 reviews. Just copy for a couple of minutes. My test, guys, is going to be so my null hypothesis is going to be a very simple one. I simply believe that this variable here is not significant, so I should not include it. So let's go to reviews. I will simply run this again. You go estimate and run the model again. Okay, can you see my equation here? And obviously, guys, from my equation, this variable here, the market information, RDGA, is very significant. You see? It's highly significant. Do you agree with me? So let's assume for now, guys, that I will ignore that. So just to test my variable. So this is my original model. Can you open, please? Open the one that says NVA omitted. Can you open this one here? Open the equation that says NVA omitted. And let's go to estimate. And you can see, guys, the only difference between this equation and this equation here is that I have removed RDGIA. I just removed the market factor. You see that? Okay. Just run. Okay. So if we run this regression, compare, guys, R squares, 0.006 versus 0.28. compare the F statistic, the probability, 0.58. So this model here is nonlinear, do you agree? So that the model tells you that you cannot reject the null hypothesis of the ANOVA, so this implies that there is no linear relationship. So this is really bad. Got it? So how do we test if one variable that we have omitted is important or not for your system? What we do is, are you with me? You understand what I've done here first? Okay. So now what I will do is I will do view coefficient diagnosis, and then you go to omitted variable. Okay. So it's view coefficient omitted variable test. Just click here, and then you write that the variable that we need to include, RDGA, should be here, minus, this is the name of my variable, day TVL. So this is the variables that I want to test. Make sense? So what I've done, guys, is I've excluded, because I wanted to show you that this variable really, if you omit this variable, your results are going to be completely terrible. In everything, guys, you can compare the coefficients. My C is completely different. My RCPI is completely different. You see that? So that's when I told you guys, if you are forgetting one variable that is crucial to your system, all your coefficients are going to be wrong. Not only the standard errors, your coefficients by themselves are going to be wrong. So that's why it's crucial when you do this type of analysis, guys, is you need to think a little and say, you know what variables I'm missing? Am I missing something that is really important? If I'm missing that, I know that everything's going to be completely catastrophic, right? So the way to test that is you simply put the variable that you want to test, and you simply run. And then here you have it. So this is my chi-square, this is my F. Okay, so my null hypothesis is that this variable here are the market factor. It's called the market factor because the Dow Jones Industrial is a market index. Implies that the market factor is not significant. This is my null hypothesis here. Do you see that? Now, based on the p-value, guys, what can you tell me? This is the F and this is the chi-square. You can use either of these ones here. 5% significance level.
You will reject, which means the factor is significant.
Exactly. And so what is next? You need to include this variable in your equation. Got it? Make sense to everyone? Questions?
Professor, just one quick question that may be slightly off topic, but
No problem.
why the Dow Jones Industrial Index? Why not something else? Is it because of is this a sector choice based on ICB classification or what?
No. Yeah, that's a good question because normally, remember, a market index, an index is basically what is called a factor, a market factor. Okay, and normally what you do is you take the index the index that where the stock is present. So, for example, this is ExxonMobil, the oil company. And ExxonMobil is part of the Dow Jones Industrial Index. So it's one of the components of the DGA, right? So that's why we select these ones here. So imagine if we talk about Amazon, okay, or Tesla. So the index that you should use is NASDAQ, for example. Make sense? So normally you select, if you have a name, in this case, what is that? ExxonMobil here, this one here. You immediately say, okay, this ExxonMobil belongs to which index? Oh, it belongs to the Dow Jones Industrial. Okay, so my market factor is going to be the Dow Jones Industrial. Got it? Makes sense? So that the market factor is the index where the normal stock belongs to.
Understood.
Perfect. Excellent. Okay, guys. So basically, this test implies that if you don't include this variable here, your results are going to be biased and are going to be non-efficient. So the worst case scenario in analysis, right? So you need to include. So the solution for omitted variables simply include the variable. Got it? Now let's do the opposite. Do you see here, guys, that we have oil, the price of oil is highly non-significant? Agree with me or not? So basically, I should remove this variable here. Do you agree with me or not, guys? Yeah, you know, what happens, what happens, guys, is if you only take a look to the t statistic and the standard error and say, you know what, oh, the alpha here, sorry, the p-value is extremely large compared to 0.05, I need to remove this one, is that sometimes there are some interaction between the variables that even though this variable looks not significant, contributes to the system. You know, contributes slightly, but contributes. One way of being completely sure that we can remove this variable without any issues with the regression here is doing the following test. So let's estimate, guys, please, let's estimate this model again, just to be sure that I have this in memory. So what I've done is I estimate and simply okay. Okay, so now what you do is you go view, where's my coefficient diagnosis and redundant variables. Are you with me? So it's view, coefficient again, redundant variables. And then here what you do is the variable that I'm trying to analyze is coil, I think. Yes, this is one here. I believe that this variable is redundant to my system. Okay, so I should be able to remove it. So, and that's the hypothesis we're going to test. My null hypothesis is that the variable, this one here, is not significant. That's my null hypothesis. So we simply click OK. And here we go. What can you tell me?
It is significant.
Okay, it is significant or not. Remember, this value here compared to 0.05. Okay, so do you reject or not reject the null hypothesis? That's the crucial thing here.
Do not reject.
Do not reject. Agree? So you do not reject what? That the coefficient is not significant. The coefficient is 0, basically. Correct? So indeed, what this model is telling you, you can be more than confident, just remove this one from your model. Make sense to you guys? Do you understand? Okay, questions?
Professor, I have a quick question.
Yeah, go ahead.
Could you just explain the difference between the value and probability columns?
Yeah, no, the value here, this is my critical value. Okay, so let me explain. Okay, so this is a chi-square 1 degree of freedom, and this is a very, very small number, right? Okay, so remember, let me share this one here. So when we have a test, okay, here my test can be I have a test, okay, and my test, we compare this with a critical value. And in EViews, I think this is called value or something like that. Okay, so if we have a chi-square, the chi-square looks like this. Okay, and the F also looks like this. So that's why one of your colleagues were saying that in normality, no, it doesn't look like a normal. The chi-square goes from 0 to plus infinite, so it never goes to a negative number, and it's not symmetric, it's like that. In order to do the test here, so normally we use 5%, so this is going to be my alpha 0.05. This critical value is here, and the test is the value that we remember when we do hypothesis testing, we simply say, okay, this value is around here. I compare it with my critical value. So this is the reject zone. And from here to here is fail to reject. You remember that? Okay, so now tell me this value. In my test for the first one, let's assume the chi-square or the F test. What is the value for the F test? In your reviews, what do you get? 0.0 something, very small.
Yeah, it's like 7.84 times 10 to the minus 5th, I think.
Yeah, so it's very zero,
That's like
zero,
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 yeah.
0.7 something. Do you agree? It is going to be extremely small, extremely small. Now, if we want to compute, this is my F, what are the degrees of freedom? Is 1 and 307, I think. Right? The degrees of freedom?
308.
Oh, 308. So if you want to find this critical value, just go to Excel. So let's open Excel. Let me open Excel. No, I need to show you. Excel, here we go. Okay, so let's do equal F dot, no, it's dot inverse probability is 0.05, degrees of freedom 1 and 308, correct? Oh, sorry, this goes to your tail. So this should be 0.95 because the tail in the F, do you remember? My tail is to the right in the F distribution. So that's why I put 0.95. So this includes from 0 to 0.95. The critical value is going to be 3.87. Okay, so this 3.87 is the one that you have in here. So my critical value, this one here, equals 3.87. And then what you do in the test is you see, okay, this is 0.000007, falls in what? In the non-reject zone. Okay, so that's why you said fail to reject. Also, remember, this implies a lot of work. Do you agree? You need to go to Excel or to another program and find the critical value, etc. But you don't need to do that. What you need to do is you need to simply take a look to the p-value, and the p-value always follows the direction of the. So if the critical is, if the reject zone is this to the right, my p-value is also going to be to the right. So basically, my p-value is going to be from here all the way up here. So that's why my p-value is 0.99. Agree? So my red one is my p-value that is equal 0.99. And obviously you can see as soon as the red region is larger than the black region, so this is larger than 0.05. So again, I fail to reject. Right? So that's the way it works. And that's why always, guys, we use the p-value. You need to know how to use this one here, but in practice, you use the p-value. Make sense?
Yeah, thank you.
Excellent. Okay, questions? Up to here is the exam, guys. So it is only OLS, the assumptions. I don't require from you to derive the equations, but I require from you to understand what you're doing. What is heteroscedasticity? What are the problems with heteroscedasticity? How do we solve heteroscedasticity? What is the issue with multicollinearity? How do we solve multicollinearity? You know, all these type of things, you must know it, okay? So the exam, I think, is going to be, I will prepare the exam in such a way that you are going to perhaps see some of the screenshots like this one. What is my screenshots like this one here? And I tell you guys, this I'm testing here redundant variable. Is COIL not significant? You need to tell me yes, no, why, and what is the meaning of that. Got it? Make sense to you? Okay, so you have the videos, guys, and just review the videos and just try to understand the videos. If you have questions, send me email and then I will answer you. So up to here, from the ordinary least squares, up to here is the second piece. Make sense? Okay. Okay, so give me 5 minutes to show you the challenge number 2. Okay, let's work with the challenge number 2. I will give you the intuition. So you need to provide me your challenges, guys, up to next week. Okay, so before the quiz next week, you need to send me your challenges, please. Nothing wrong, nothing bad if you work in groups. Okay, nothing. Just try to solve it and try to understand it. What I will give you is the intuition, and that's it. Now, everyone, please, for the challenges, you need to create please do this. The naming convention is going to be challenge 1 underscore your name, your surname. Okay, no, it was Excel, was this one here? WF1, I think. I don't remember. The ABUS extension. And challenge 2, your surname, the same extension, ABUS. Got it? Make sense? So, okay, let's talk a little about the challenge and the idea of this one here. I will show you this in Excel, but you can do this in ABUS, okay? So this is the data, guys. Sorry, I need to show you my screen. You see my screen? Okay, so what is interesting here, guys, is a simple time series of dollars. So this is the amount of dollars that the toll simply collects in a given month. And this one here is simply my number of months. So what I want to see, if I plot simply the dollars versus the month number, it's a time series, you agree? So you can see this is the number of months, and these are the revenues in dollars. And then if I tell you guys, the only thing that I want to know is what happens between 36 and 40. That's all. I want to tell you what's going on with 46 and 40. So and this is a real life example, guys. And it was I did a consulting here, and the one that called me told me that simply the forecast of the people that was working with this model was terrible. Okay. And then I asked for, okay, give me what they are doing. And I'll say, okay, we're doing an OLS. They didn't do that, even a graph. So they would simply apply the OLS model for this one here and run the OLS. So basically what they did is this one here. You see, if you run the OLS, guys, we have done this in the previous example classes. You simply right click here, trend, and then simply linear trend. This is your regression, guys. It has a negative slope. The R square is extremely small. But also you can see what is the forecast, guys, according to your model if we go to 36. Obviously, this is going to continue going down. Makes sense? It's like an extension of my line. Agree? How do you feel about this forecast? Terrible.
It's very inaccurate.
Yeah, completely terrible. Do you agree? Really is bad. Why? Because if you are in the industry, guys, you realize, come on, my revenues are going up. How are you going to be forecasting that this is going to go down by a lot? That doesn't make sense. Correct? So okay, so that's why, guys, when you do an analysis, just try to do a graph, try to understand the data. That's why we do descriptive statistics. So all the time we start with descriptive statistics because we need to understand what's going on here. And what happened here is, and you can observe here that it was going up and then suddenly it collapsed. And then, after some time of kind of being stationary here, then it started moving up again. What happened in this year here, there was a change in policy. I don't know what was the change of policy. I don't remember at this point. But there was something that basically avoided that the people that were using the highways, they simply avoid the highways. I think they increased by a lot the toll fee. So instead of moving by the highway, they start moving towards the city. Something like that happened, okay? And then the people get used to the new toll, and they start coming back again to the highways, and this happens also here. Okay, so this is the way you do your regression if you just simply run the regression as you want. But there is something that is really interesting here, guys, and this is related to dummy variables. Okay, so let me show you what happens here. I will present you some context on dummy variables because that, believe me, guys, dummy variables help a lot. Okay, in very complex situations, dummy variables can also give you some guidance. It's not good for everyone, not always good, but it can help you. So imagine, guys, the following. Okay, so let me talk about dummy variables. Okay, so in terms of dummy variables, guys, imagine that I have the following graph. Okay, and then suddenly, okay, so suddenly something happened here. you can see here, guys, that if I do a single line, if I try to do a knowledge model, my line is going to be something like that. You agree? Not good. Not good even for in-sample forecast. It's not fitting the data correct. It's doing what the model is supposed to do, but it's not doing the correct work. But you can see that the slope appears to be more or less the same, but in different regimes, correct? So the base estimate can be something like, okay, I want to have a line here, and I want to have another line here. Okay, so how do we create this stuff? So this is case A. Slopes are the same. Okay, so if the slopes are the same, so my general model, guys, is going to be yt equals beta 0 plus beta 1 x1t plus an error. So this one here is my red line. Okay, this is the one that creates my red line. Now, if I want to create something that produces the blue lines, what I will do is I will define a variable d, okay? And I will say simply d1, let's put this here, tau, a date, any, before tau, and 0 otherwise. Do you agree? So basically what I'm doing, guys, is technically, if you imagine your Excel, for all the observations before time tau, I will put 1, 1, 1, 1, 1, 1, and after that 0, 0, 0, 0. Guys, so I'm creating a new column. That's all what I'm doing. Now, and my new model, guys, is going to be yt equals beta 0 plus beta 1 x1t plus beta 2d plus my error. Got it? And now take a look to what happens. Take a look to what happens. So this is my new model. Now, guys, here you can see that I have a d that is a binary model. It's a binary variable, can have 1 or 0. Got it? So what happens before tau? Before tau, I know that d equals 1, right? That's the way I have defined this one. So if d equals 1, my model is going to be equal to, okay, this is my y hat, is going to be equal to beta 0 plus beta 1 x1t plus beta 2. Agree with me or not? Because d is 1, so times 1, d is 2. So my estimate value is going to be beta 0. This is a constant, so I can add up to this one here, plus beta 1 x1t. So as you can imagine, guys, what I'm doing, I'm simply modifying here the slope, the y-intercept. This can be high or low. It will keep the same slope. This is my slope. But what it will do is will go up and down. So what happens after time t? We can understand that. What happens after time tau? After tau, my d equals 0. Correct? If d is 0, this part here disappears, and what I get, yt hat equals beta 0 plus beta 1 x1t. Make sense? So now, how do you expect B2 to be, guys? Positive or negative? So remember, when we are in period 2, my intercept is going to be higher. Do you agree? Agree with me or not? So how do you expect beta 2 to be? In this example, how do you think beta 2 is going to be? Positive or negative? So remember, okay, so let me do something. I will do an extension of my line. Okay, so of this blue line here. And I know that that corresponds tau after tau, so it's d0, so this is beta 0, correct? Agree with me or not? Guys, follow me for a minute. This is beta 0. Agree? remember, this blue, this part here corresponds to tau large or dates larger than tau. So the way I define D is 0. So this is beta 0. Agree with me or not, guys? Good. Now, what is the slope? Sorry, what is the y-intercept of the first part? So let me do this in a different color. So what is the y-intercept here? I'm below or before tau. So my slope is going, sorry, my intercept is going to be beta 0 plus beta 2. Correct? Guys, agree? Okay, so now, which one is larger? Beta 0 or beta 0 plus beta 2?
Beta 0 plus beta.
Beta 0. They agree beta 0 is larger. Of course, come on, guys. This is simply the distance, the height. So how beta 2 should be? Positive or negative?
Negative.
Negative.
Negative. And the reason is that. Now, how can you know what to say that this is so confusing. So how can you have beta 2 to be positive? What do you need to do in order to have beta 2 positive? What you change is simply the definition of D. You can say, you know what, 0 before tau and 1 otherwise. And that's it. You simply, it's up to you. The only thing that you need to remember, guys, is how do you interpret your results? And I have to stress this one here because a lot of people confuse it. They always say, oh, beta 2 should be positive. No. It depends on how do you define this variable. Okay? Make sense to you? So please note that beta 0 is smaller than 0 because I have defined my variable in this way. If you define D 0 and 1, beta 2 is going to be positive. Make sense? Okay, good. So this is
I just
case
have
number.
a quick question.
Yeah, go ahead.
How does it always work with D being valued as 1? Like I don't understand how you're able to just basically choose whether beta 2 is positive or negative. Like it doesn't have its own inherent value.
No. It has its own inherent value. So if you run this regression in EViews, beta is going to appear a number. It's going to give you a number. Okay. The only thing that I'm telling to you is that if it appears less than 0, don't panic. Yeah, it can be less than 0 because you have defined your variable D in this way. Right?
Okay.
So it will be a value. You're going to compute a regression and appear a beta. We're going to see this in the challenge number 2. So that's why challenge number 2 was very nice. Make sense?
Yeah.
Okay. This is case number 1. Copy and then we can do case number 2. Ready, guys? Okay, so now imagine, guys, that you don't only have that everything is changing. The slope here looks like, sorry, the slope looks like this for this part here, and the slope looks like this for this part here. And also you can see that the y-intercept is different. You see? So your initial model, guys, if you run the simple OLS model, your regression is going to be perhaps something like that looks like that. That is bad. Agree? So this red graph comes from the simple model yt equals beta 0 plus beta 1 x1t plus my error. Okay, so this is my red line. So of course you know that come on, this is not good. How do you create different slopes and different intercepts? What you do, guys, is that again you define your variable d. Okay, I don't want to confuse you, so I will define it in the same way. 1 before tau and 0 otherwise, so after tau. And my model, guys, is now going to have the following form: beta 0 plus beta 1 x1t. Okay, remember my slope is different. Sorry, my intercept is different. So what I will do is I will create beta 2d, like here. My y-intercept, remember, here. This is for controlling for different intercepts. But also, my slope is different. So how do I do that? I do multiplicative factors. So this is beta 3 x1t plus et. So this controls. So this part here controls changes in slope. And this one here controls for changes in intercept, y-intercept. Okay, so let's understand again how this works. So if we are before tau, so this implies that d equals 1, correct? So if d equals 1, guys, my equation, this equation here is going to become what? It's going to be yt equals beta 0 plus beta 1 x1t plus beta 2 plus beta 3 beta 3 x1t, correct, guys? Do you agree? Because it's 1, d is 1. So this is a constant, goes with this one here, and this has a common factor x1t. So I can aggregate this one here. Beta 0 plus beta 2, this is my new intercept, plus beta 1 plus beta 3 x1t. So this is my new slope. Do you see? Now, what happens after tau? So this implies that d equals 0. So my model goes to, so the ones that have d disappear. I end up with beta 0 plus beta 1 x1t. And that's it. So now I'm controlling for everything.
So you've set up your dummy variable based on the values of your beta 2 and 3.
No. My dummy variable is
What is
dummy.
that?
I simply 1 and 0. Simply is position. Okay, it is simply position. So it is based purely on positions and on understanding when tau happens. Okay, Now you can have multiple dummies, guys. You can have as many dummies as you want. However, there is one issue you need to be careful. Questions up to here? Okay, so you can create these fancy models with very simple dummy variables. Of course, later we can, I don't know if we have time, but we can do Markov switching models or more complex models, but these ones here really make very good results. Okay.
Professor,
Yep.
I'm still a little confused about kind of what's been talked about already is like substitution, right? So like where you can and can't substitute your dummy variable. I'm still not getting it.
When you can, no. This is data. You have data, and what you want is you want to create blue lines like this. Instead of the red, you want to create blue lines like this, okay?
Right.
So the first thing you need to acknowledge here is that the slope in the first part is completely different than the slope in the second part. One is steeper. And the other thing that you need to acknowledge is that indeed the y-intercept for the first part is around here, and the y-intercept for the second part is around here. So you have different slopes, but also you have different y-intercepts, right? That's what you want to model. So the solution for this one here, this type of problems here is very simple. What you say is you identify first tau. When this happens, more or less, oh yeah, I know that this happened around tau, got it? And then I created a dummy variable, D. And the dummy variable, guys, I will show you in the Excel example. It's simply ones and zeros, that's it. Okay, and then you say, okay, I will call, this is up to you. You can call 0 or 1 if you want. It's up to you. I said 1 is the before and 0 is the after. And then you create your new model. Your new model is going to be like this. You add beta 2 times D. Remember, this one here controls for the y-intercept. It's a constant, so there is nothing here. And this one here, when you have this product of D times x1t, considers the changes on the slope. Okay? And then basically what you say is, if I'm in period 1, so I'm in this period here, so this implies that D equals 1, correct? Do you agree with me? Because that's the definition of my variable. So if I have data here, so I'm in this period, I'm in the left of at the left of tau. So at the left of tau, I know that D equals 1. Do you agree with me?
Okay.
You agree?
Okay, yes.
Yes. Okay, so if D is 1, just replacing your equation, if this D is 1, so beta 2 is going to be beta 2, degree, times 1. And also this one here is beta 3, 1 times x1 is beta 3 x1. And then what you do is you simply collect the terms. This is a constant, this is a constant. You can sum them. And this has a common factor x1t. You simply sum the coefficients, and then you have this one here. So
Okay.
you can see, that this is my new slope, and this is my new, this is my new y-intercept, and this is my new slope, compared to this one here. That happens when we are in a period to the right of tau, in this part here.
Okay, and then you get the red line, right?
No. The red line is where you, no. Forget about that. This one here now, as soon as this model belongs to this model, so this one here, remember, yeah, looks like this one, looks like the red line, but it's not the red line anymore because the model has computed, the model you have run is this model, it's not this model here. This model here looks like this, but remember, comes from this model. It doesn't come from this model here. Okay, let me show you. You're gonna get this one here in the example in that I will do. Give me 1 second. I'm pretty sure you're gonna get it.
Okay.
Okay, so let's go now again to our Excel file. Basically, guys, what we are saying here is that the red line is this one here. So this is what was the red line. Okay, so how do I get this red line that is terrible? I simply run my OLS model. So my my variable is going to be, my y is this one here, and my x is this one here. If you run that model, so this is what you get. Your R squared, this is not that one. Let me see. Yeah, this is the one. So basically, guys, you obtain something that is like this. It's terrible. Okay, so but then you realize, hey, wait a second. I remember that if I have a break, this is called a break. Okay, structural break sometimes. I know that something happened in this period here. Okay, and happens that this happens exactly during the first year. There is a change here. So what I've done is I define the following. Take a look. So this is the data as usual. And I created a dummy, this D. And how I define the dummy, I said, okay, you know what? Every observation that I have before the first year is going to be named 1. And everything after that is going to be called 0. So this is my dummy. Make sense to you? So this is the dummy that I'm writing. So now my model is not going to be anymore this one here. Sorry, it's not going to be simply my y and my x. My new variables, my new model is going to be, I think I have it here. Oh yeah, we have it here. It's going to be, just to be sure that you understand, let me redo the regression here. We'll do the regression. So what I will do is I will run the regressions. So let me move this one here. Let me move this one here. You do data analysis, you do your regression. Of course, in EViews, you do this different regression. And then what is my y variable? My y variable is the US dollars. So it's all this part here. And what is my x variable? My x variable are going to be these two things. Okay, so I have labels, my output range. I want my output range to be perhaps here. And then I simply click OK. That's the regression I've done. Do you see that? Guys, do you see that?
Sorry, Professor, if you don't mind just doing a quick rerun of that.
Yes. So what I've done is the following. I've done data analysis, the regression, and then I've selected my Y. My Y is my revenues, the US dollars. You select only the US dollars. And then what are my X's now? I have two X's now. I have the month and the D. So you select these two. And then you simply run the regression.
Thank you.
Okay, perfect. Then if you run the regression, the results are these ones here. You see that you have a coefficient for D. Okay, so basically what I'm doing here, guys, is I'm doing something like this one. What I believe is that I keep my same slope. I'm doing this one here. So I've run this model here. Do you agree with me, guys? And then when I obtain my results, I obtain beta 0, I obtain beta 1, and I obtain beta 2. That's what I obtain. So these values are this one here, are these values here. All of them are significant. This is 0, this minus something. So it's basically 0. So they are highly significant. There is a linear relationship, and my R squared now is, instead of 20, do you remember, 0.03, now it's 20%. Sorry, now it's 94%. And then you can take a look, guys, to the graphs. Take a look, guys. We don't have anymore the line that was like that. Now we have two lines. I have one line here, and I have another line here. Make sense? So what I've done is I've broken my linear regression. So I have regression linear in two pieces. Same slope, different intercepts. That's what I've done here with this model here. Okay, so that's what you need to try to do. Now, just to show you guys something more, okay? Questions up to now?
I have a quick question, Professor.
Yep.
So when you're part of the challenge 2 is to try to predict the next US dollars that was coming up. And I'm
Yeah.
curious, would it make more sense to make a regression with only the dummy, like the values that have a dummy variable of 0 and go from there, or to use the adjusted regression with both month number and dummy variables acting as x's?
Yeah, you need to do that. You know
Okay.
what? Let me say, yes, you know what? It is better to have the complete data set because the complete data set provides information. Yeah, I remember it worked. You know, it's much better is this one here.
Okay, thank you.
Okay, now guys, just to show you something more, someone can argue, you know what? But also I believe that there was a change during the last 6 months. And actually this was a change. There was another change in rules. I think they decreased the toll fees. So the last period here, if you believe there was something here, you know that there was something here, another structural change around here. What you can do, guys, is you can create an additional dummy. You agree? So what I've done is I've broken, it's during the last 3 weeks, months, there was another break. So then now I don't have only D1. D1 is this part here. But also another, you see these 3 months, they jumped and they do something particular. Apparently the slope is different here. So we created a second dummy, this is D2. And then you simply run the regression. So you now have the number of months, D1 and D2. And then you can see the result is something like that. You see that? So before your forecast was going to be around this part here. If you go here, it was going to be, in between this blue here and this blue here. It doesn't look very good. But if you simply go this one here, you can have a better forecast. Just analyzing this one here. Now, if we see all the graphs, this is the first one. OLS model is terrible. The simple OLS model without considering breaks is terrible. This is much better. Do you see? Just having 2 breaks is much better. But also analyzing the data, knowing the data, and seeing that you have not only 1 break, but you have 2 breaks, it makes much perfect forecast, guys. Okay, so I want you to try. I want you to do your best and try to understand how we can manage this stuff. And after that, you're going to have this Excel file for your records, and you're going to start working with this and thinking with this one. But try. It is just try to do it. Okay, questions? So I need to move to time series now.
Just a quick question.
Yeah.
So in order to get the estimated value, we have to plug in the variables we got from the test into the equations we got before tau and after tau to get the estimated value.
Yes. So the estimated value, remember, if you see this one here, it's simply like this. If K41 is equal to 1, so that's what I'm saying. If this number here is 1, okay, so you use the complete equation, correct? So it's going to be it's going to be the intercept, J34, plus J36 that multiplies the month, plus the other one. So you do the complete equation when D equals 1. If D equals 0, you can see that the regression simply gets smaller. So you only take the intercept and the month and the number of months. That's all. And so you simply
So
got it?
so the formula is the same, but just that the value of D is different.
Yeah. Oh no, the formula is exactly the same. It is exactly the same. It's like D is a new X. It's like a new variable.
Okay.
Okay. Perfect. Okay, guys. So hopefully we're going to have more time to do this. I think challenge number 3 is going to be more challenging, just using this type of structures. Okay, so let me go back to my share, and then I need to move. So dummies are not going to be, I think are not going to be part of the exam. I don't think so, but just understanding dummies and really, dummies are really useful for everything. When you have, for example, gender, okay, and want to model gender in an equation, this discussion about income between genders are different. Okay, so we can use male and female. This type of variables, you can say male is 1, female is 0, or otherwise. Okay, you can have dummies for this type of variables that are qualitative, not quantitative. So this works like that. Makes sense? Unfortunately, we don't have time, guys. I need to continue moving with the class. Questions? Okay, so let's go. So now we start time series. Hopefully you have had time to read and to watch the video, guys. And let's start first with univariate time series. Okay. The main concept here in this type of models, guys, is what is called stationarity, as you have read from the presentation. What we need is to be sure that we have a stationary process. So what is stationarity, guys, in words? Simply means that, for example, this one here that looks like stock exchanges is not a stationary process for the following. If you just take one interval, okay, and assume that you take another interval the same size, okay, that the trick is the size of these intervals are the same, and just compute the mean here. Perhaps the mean is going to be around here, correct? And the mean of this process is going to be around here. So stationarity, guys, implies that all the moments on the distribution are exactly the same. If you just take a look to these means are not the same, so basically this process is non-stationary. When you have non-stationary processes, guys, you cannot use the models we're going to be using in a couple of minutes. Okay. The condition for the time series models that we're going to be developing here is stationarity. And there is one special type of stationarity that is called the weak stationary process, weak stationarity. So what is the definition of weak stationarity, guys? Is basically that the mean of my process exists, is mu. The variance of my process, the variance of my process is a constant and exists, so that's why it's minus infinite. And the covariance of my process simply depends on the distance. Okay, it doesn't depend on a time frame. It depends on the distance. For example, the covariance of y1 with y10 is going to be exactly the same as the covariance of y, let's say 21, y30. Okay, so the distance here is 9, well, it's 10, and the distance here is 10. So what matters is the distance. If we take two intervals and we compare them, the covariances are going to be the same. And in this case, my covariance is going to be called gamma 10. Got it? Then, guys, I talked in the video about ways of finding correlations, autocorrelations. I talk about the long box, the box pairs, etc. And then I start talking about a couple of models. I start talking about an ARP process. So let's start talking about the MA process. I start talking about the MAQ process. And I was telling you that MAQ process is simply a process that looks like that. So mu is the mean, the conditional mean of unconditional mean of YT. And then this is going to be plus UT plus theta 1 UT minus 1 plus theta 2 UT minus 2 plus theta Q UT minus Q. So this was the MAQ. So what is UT? This is simply a white noise process with zero mean. What is a white noise process, guys? It is a weakly stationary process. And the condition of this white noise process, guys, is that simply that the mean for this process here is going to be 0. The variance of this process is constant. And the covariance of these errors is always going to be 0 for all j different than 0. So this is the definition of the white noise process, guys. Everything is well explained, please, in the video. So you need to take a look. It's 1 hour, 30 minutes video that it explains in detail every single every single part of what we are doing here. So this is my MAQ process, and I told you guys that this MAQ process can be written as a mu plus, okay, I will say mu t plus theta 1 L mu t. So remember, this is a time multiplier plus theta 2 L2 ut plus theta q L to the q ut. So if we take the common factor here, this is going to be simply equal to 1 plus theta 1 L plus theta 2 L squared plus theta q L q ut. And then if you summarize these numbers here, normally what you're going to find is simply, this is the notation, the compact notation of my model. Okay, it's simply, this model implies simply that my variable yt depends on previous errors. So the time series of the errors are able to explain the behavior of my model. What was interesting about this one here, guys, is the correlation function. So what is called the ACF, the autocorrelation function, disappeared. It was different from 0. So basically, guys, it's going to be different from 0 for lags smaller than q. And it's going to be equal to 0, smaller or equal than q, for lags larger than q. Okay, and this is the tricky part. This is the interesting part here, guys. If you see your ACF, okay, I've done this horizontally, but I'm doing this vertically. But for example, if you see something like that, and then disappears, what type of process do you have here? As soon as this is my ACF, okay? And if my ACF has 1, 2, and 3, so this implies that I have a MA process, do you agree? Because the ACF, the lines disappear. After that, this goes back to 0. What is the order of my MA, guys, according to this graph?
MA3.
MA3. Exactly. Why 3? Because after 3, simply my autocorrelation function goes to 0. Right? So this is the main characteristic of my MAQ process. Right? If you want to identify a MAQ process, simply take a look to the ACF, and then if you see that the bars go quickly to 0, and then they stay at 0, you simply count the bars that are different from 0, and this gives you the order. Okay. So the next process, guys, that I talked about in the video is what is called the autoregressive process of order P, RP. Okay, the RP, guys, is simply a model. So this is the same. Then I have lags of the endogenous variable, this one here, plus psi p yt minus p plus my error. This one again is a white noise process. Then if I rewrite this part here, I move this part here to the other side, this is going to be yt minus psi 1 yt minus 1 minus psi 2 yt minus 2 minus psi p yt minus p, and this equals to my constant mu plus my error term. Again, if I do some operations here, so this is minus L yt minus psi 2 L squared yt minus psi p L to the p yt equals mu plus ut. And then from here, guys, common factor is yt, so it's going to be and this is equal to mu plus ut. This is mu is different. And then finally, this one here, normally is noted, it's written like this one here. Okay, what is crucial from these R models, guys, is something that is called stationarity again. Okay, and the stationarity condition requires that all the roots of the characteristic equation basically the characteristic equation is this part here, 1 minus psi 1c minus psi 2 c squared minus psi p c to the p equals 0. So basically all the values that satisfy this condition lie outside the unit circle. So in words, guys, what we want in order to ensure that we have a stationary process is that each of the c values is larger than 0. Right? So let's assume the following. How can you write an AR1 process? How do we write an AR1 process? Okay, 1 minute to copy, then we continue. How do we write an AR1 process? Someone can tell me? So this is a generic ARP process. So what is an AR1 process? So this one means what, guys?
Would it be yt equals mu plus psi sub 1 y sub t minus 1 plus ut?
Exactly, that's it. Do you agree? So this T1 implies how many lags of the same YT? 1 lag. Right? So that's all what it means. Now, I will rewrite this one in this form. If I rewrite this in this form, it's going to be YT equals, minus psi YT minus 1 equals mu plus UT, correct? So there is a lag operator that is called L. So what we need to remember, guys, is that just in here, if I do LYT, so this implies simply YT minus 1. If I do L cube YT, this implies simply YT minus 3. So this is the L is the time operator. Okay, so if I continue writing this equation here, common factor is going to be YT, it's going to be 1 minus psi L YT equals mu plus UT, correct, guys? Now, stationarity condition, focus on this part here. Okay, so what is called the characteristic equation is simply you replace the L by C and equal this to 0. And then you solve for the values of C. You know, if you have a quadratic, you have a quadratic, you have 2 values of C. If you have a cube, you have 3 values of C, and so on. So, but this one here is very easy, do you agree? What is C is going to be equal to what? I move C to the other side, it's going to be equal to 1 over psi. Correct, guys? And if my process is stationary, if my AR1 is stationary, this implies that C in absolute value must be larger than 1. So this is the meaning of outside the unit circle. Okay, remember when you have a circle, the radius is 1, a circle of radius 1, got it? And the value can be positive or negative. So that's why we use the absolute value. And the absolute value of C must be larger than 1. But what is interesting, guys, is that C larger than 1, and you know that C is equal to 1 divided by the coefficient, is exactly the same as requesting this one here being smaller than 1. Yes or no? Do you agree with me? Yes. So the stationarity condition implies, guys, that your values in absolute value psi, so that the one that you have here, this is psi 1. Sorry, I'm forgetting psi 1. Psi 1 is going to be strictly smaller than 1. And you're going to have a stationary process. Now, guys, remember in the example I give you in the video, hopefully you have watched the video, I give you 3 examples. If psi is larger than 1, this is an explosive system. Do you agree? So it's simply once you move this from the mean, it goes up, 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 or down, down, down infinitely. So there is no solution. There is no equilibrium when you have an explosive system, non-stationarity. Now, what happened when you had this number equal to 1? Once you move it outside the equilibrium, it stays there forever. So basically, what I'm saying is that imagine that you have a series that is moving around here. And then suddenly there is a shock, and this one here is going to go, for example, like that forever. Got it? So then there is never going back. This is an explosive system. When psi equal 1, this process is called unit root. Also, it's a non-stationary. And so what happens graphically, guys, is the following. So this is this, this is this. What happens is, imagine you have your process moving around here. There is a shock, and then it moves here, and then it stays there forever, never goes back. So this is a unit root process. And what is a stationary process? Basically means in absolute value, well, let me put absolute values. This is smaller than 1. So this is a stationary process. And a stationary process, guys, looks basically something like that. And if you have taken a look, guys, this looks very, very like a returns, for example. Do you agree, guys? Do you understand? Okay, let's do e-views. Guys, please, this part here, you should watch the video. Okay, there is a 1 hour, 30 minutes, guys, that I invested for you. So take a look to the video. Every single detail is explained at a minimum. So you just go watch the video, please. Okay, so now let's go. Let me share you. Can you open another Excel file, another e-views file? I sent you today, I think. Yeah, the name is ARMA Alcoa. Oh, wait. Before going there. So what is one of the properties of the R process, guys? If you see in RQ process, the autocorrelation function, what the autocorrelation function of the AC or the RP process looks like. Well, in this case, guys, the RP process is going to be like that. Continuous, continuous, continuous. So it basically goes down, 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 down. Okay? So it has this behavior. It can go up and down also, but it has this behavior. It doesn't disappear like a MA process. Got it? So if we see an ACF like this, oh, got it, I know this is an R process. What is the issue? What is the P? Remember in the MA process, it was 1, 2, 3, disappeared to 0. Do we know that it was an MA3? Remember that? But in this case, the ACF simply goes infinite. So it goes down, 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 but never goes to 0. So how do I recognize what is my P here? Okay, for that, we need something that is called the partial autocorrelation function. Okay, and what is the partial autocorrelation function, guys? It's simply the correlation, for example, of yt with yt minus k, after we have control for yt minus 1, yt minus 2, yt minus k minus 1. So what I've done is I've controlled for all the intermediate steps or intermediate lags, and I want to see what is the correlation between this and this. Okay. So in the MA process, take a look to how we can measure that. Remember the MA process, guys, is simply UT equals mu plus 1 plus theta 1L plus theta 2L squared plus theta Q LQ that multiplies UT. Okay, now this one here is indeed mu plus theta L UT. Then assume that this one is 0. Okay, just assume 0. Just for making it easy. So then YT, if I want to know this one here, I will do is theta L to the minus 1 equals UT. Do you agree with me or not, guys? So this is a series. You go to the minus 1, and then you obtain this one here. However, guys, this is a geometric progression. Goes to the infinite. Right? So basically, this one here, it will be going yt theta yt minus 1, theta yt minus 2, theta yt minus 3, theta to the infinite. Got it? So that's why an MAQ is equivalent to an AR infinite. So an MAQ process, guys, is equivalent to an AR process infinite lags. So that's why for the MAQ process, guys, the partial autocorrelation function will look like that. So it will go like that. So the PACF of a MA process looks very similar to the ACF of an R process. What happens with the ARP process? So remember that my ARP process is my ARP process is simply mu plus psi 1 yt minus 1 plus psi 2 yt minus 2 plus psi p yt minus p plus plus ut. Do you agree? So what is the direct impact? How many lags directly impact yt? P lags, do you agree? So how many autocorrelations I will have? Partial correlations I will have. How many partial autocorrelation functions I will have? I will have P. Correct, guys? So basically the partial autocorrelation function of an ARP process is going to look like this. For example, this is the partial autocorrelation. So you know that the partial autocorrelation goes to 0. So we talk about an AR process. How many lags in this AR process? Guys, how many processes? How many lags?
4.
4. Got it? So let me summarize this one here. We're not going to have time to go to the videos. Okay. So in summary, guys, I need to summarize this for you. In summary, guys, an MAQ process versus an ARP process. The autocorrelation function for the MA process looks like, for this one here, looks like, goes down like that. This is ACF. The PACF for the MA process looks like that. And for the PACF for the AR process looks like that. Okay? Makes sense? So what process do we have here, guys? Exact process according to my graph. MA what? And AR what? First of all, you know that this is an MA because the ACF stops at 2, and then the PACF goes like that. And here you know that you have an R process because the ACF goes geometrically declining, but the PACF decreases or disappears after certain lags. Agree? So that's the way you identify the model. So this is an MA what, guys?
2.
2, perfect. 1 and 2. And this is an AR what? AR what?
4.
4, because you look 1, 2, 3, 4, and then goes to 0. Okay? Now, there are a mixture of models that the model is called ARMA PQ. So how the ARMA PQ is basically the combination of both. So my ARMA PQ, guys, is going to be equal to, this is my constant, plus psi 1 yt minus 1 plus psi p yt minus p plus ut plus theta 1 ut minus 1 plus theta q ut minus q. So this is a mixture of, and of course this one here is my white noise process. So it's a mixture of both processes at the same time. Got it? You see this part here is my RP, and this part here is my MAQ. Correct? So the ARMA PQ process, guys, simply uses a mixture of these two processes. Now, how do we identify an ARMA PQ process? The ARMA PQ process, guys, has the ACF and has a PACF that look like that. etc. So goes like that. So if you have the ACF and PACF that look like that, so you know that you know an ARMA process. What is the problem with this one here, guys? The problem is that you don't know the lags. Agree with me? So you know, oh, I have a mixture of processes. But then the question is, okay, but tell me, what is the number of lags here and number of lags here? You have no clue. Got it? So you have no clue. So you don't have an idea. Okay, I know that I have an ARMA, but which ARMA? Got it? And in order to select the model, guys, we're going to use, in order to know what is the lags, what is the optimal number of lags, we are going to use something that I call the information criteria. Okay, and we are going to use basically two. The Kaike information criteria, and we're going to use the Bayesian Schwartz, or also called Bayesian information criteria. Okay, so the formulas are basically ln of sigma squared plus 2kt, or ln of sigma squared plus kt ln of t. And what you want is you want to minimize them. And this is something we're going to talk later. Okay, so we're going to rely on two criteria. There are three, but I think two are more than enough. And with that, we are going to be able to select between the ARMAs. Okay. If you can please review this information, next class we're going to do the EViews, and you're going to see this is clear. It's going to be extremely simple. You're going to see EViews time series is going to be done in 10 minutes. Please review, okay? Review. Now, a couple of questions. How many classes are you taking during this term? Do you have classes on Wednesday, Thursdays? Yeah, and what about Fridays? You also have classes on Fridays in the afternoon or evening?
Morning.
And what about the evening, like 5:30, 5, 4?
Yes, classes on Thursday at 5:30.
And Friday? Someone has classes on Fridays, guys, at the same time, 5:30?
Yes, I have class 5:30 to 7:45. Yes.
Yeah. Okay, there is nothing to do. Yeah, well, in that case, I need to compensate. I need to do more videos for you. So because we have the exam, and during the exam is basically we don't have time to do more. I will try to do something perhaps next Tuesday. I will try to finish the time series in EViews, that is very quickly. Then we do the exam, the quiz number 2. Got it? So we gain some time, and then I will provide you another video for garage models. And then we continue moving. But you need to take a look to the videos, guys, please. Otherwise, we cannot move. Make sense? Okay, so study, please, be prepared. And this is for you guys. Remember, all what you learn here is for you. It's not for me.
Professor, quick word after class.
Yes, of course. Okay, guys. So see you in a week. Study. If you have questions, please email me, and then we can do a review. Or we can meet perhaps 30 minutes before, and then we can do a quick review. You just let me know. Okay, guys. See you later then. Please study. Okay, study. There's no way to learn this stuff. See you guys. Take care.
Thank you.
Professor,
Thank you.
quick question.
Yeah.
So the
Give
quiz
me
is
one.
not-
Give me 1 second, please. One second. I need to.